Hello and welcome. This is my presentation for my final project for the CSCIE 118 course. This project is essentially an anomaly detection project where I have attempted to predict blockchain fraud using various machine learning techniques. So why anomaly detection? One of the major reasons is that crypto values are trending up, and there's a lot of buzz in the industry about crypto, and there's more people jumping on various platforms and getting involved. And so obviously that's a motive for bad actors when there's a lot of transactions and there's any sort of value moving around. You can expect bad actors and their interventions within the system. So because of that, InfoSec teams around the globe need to get ready for this essentially nascent framework across the different blockchain platforms. The other reason too is with the advent of machine learning open source software, there's a lot of new opportunity in this area. And a lot of overlap or intersection with blockchain and anomaly detection using classification. So that's essentially the methodology being used is supervised learning, supervised classification models. Specifically in this project, to keep the scope limited, I've used decision tree, a logistic regression, a random forest, and a gradient boosting algorithm. And try to base my model selection on the correctness of the recall score, as well as the number of false positives. And we'll talk about it a little bit later and also take a deeper look into that. So the pipeline, the ML pipeline or the architecture is something like this. So it starts with a data frame sourced from Kaggle. So it has about 50 features and then a label column, which is essentially our flag for fraud. And that's obviously a binary 1 or 0. A lot of EDA that follows that, including visualization using a lot of the standard libraries. And then some feature selection based on, common sense, business logic, as well as a couple of statistical techniques like chi-square and ANOVA. And then, some feature engineering that has to be done, splitting the data into the train and test, and then applying these model algorithms to then cough out a function that essentially can be used then to make the prediction on the test data. The hyperparameter tuning, even though this is from my original proposal, where I intended to use ParamGrid and cross-validator, I ended up customizing and creating my own tuning function just to keep the scope limited to what I wanted to do. And so we'll go over that in detail as well. And finally, we look at tracking and selection. So with that, we'll jump over to the actual Jupyter notebook where I've written my code. So the first thing is to import all our libraries, pretty standard libraries here, pandas, NumPy for all our manipulation, and sklearn is really the meat of our stack, which we've used various different things from sklearn's feature selection, model selection, their models themselves, the linear model, the tree models, and the ensemble models. And then especially for the evaluation, sklearn provides very nice metrics. Seaborn and Matplotlib are going to be our graphing libraries or visualization libraries that we've used here. So coming to the EDA, the first thing is to really look at the shape. So you can see the dimensions here. It's got about 10,000 rows and 51 columns. Taking a look at these columns, you see there's a whole group of identifying the transactions, then going into the time related features of the transaction, then value related information about the transaction. But that's essentially the high level overview of the data. And then we do a dot describe to understand some of the central tendencies, mean, the 25th percentile, 50th, 75th percentile, And this actually tells us that there are some of these features that have only zeros in them. And so in the next section, really, we've just taken those out here. Then we'll look at the schema here. So looking at the schema, you see a lot of floats, ints. We get rid of the objects just to keep the scope limited. Certainly these objects can be treated and indexed or one-hot encoded as well. That's another way to handle them. Then we're looking at this flag column, which is our label column. So we're looking at the balance here. So you can kind of see the balance here is, it's about 22%. There are various different schools of thought on how to handle this. One school of thought is don't do anything, don't change anything in order to mimic real world scenarios. In this case, we haven't done anything, mainly because the balance isn't that bad. Usually you see an imbalance, where the label column, you have just, maybe 1% or less than 1% that has the value equals 1. And in this case, we have 22%, which is great. But if we didn't have so much, one other option, if we didn't want to leave it as is we could do some minority oversampling, which essentially is just taking the minority here and either you replicate them or you create various versions of those minorities so that the data can be a little bit more balanced. One such way of doing that is called SMOTE, which is synthetic minority oversampling technique. That's outside the scope of this project, but it's worth considering and maybe can be put on the roadmap for this project. I've dropped the NAs here. Again, a lot of things can be done with the NAs. You can replace them with central tendencies, like the mean or the median. But for the purpose of this project, I've just dropped the NAs. Looking at the correlation between the features, really the main thing that we want to see here is, the flag column. We want to make sure that there's nothing, and this is in the form of a heat map. So anything that's closer to red means that the correlation is very high, 1.0 being dark, deep red. So really, we want to make sure that no feature is very highly correlated with the flag column, because in that case, if there was a feature, let's say this feature send transactions was red here with flag, what that would mean is that that's sort of a giveaway. And when we train the model can use that to sort of quote unquote cheat and say, okay, well, I'm just going to really heavily weight this send transaction feature. And that may not be useful for us. So we don't see any, patterns here that are unnerving. For example, some of these reds and oranges, it makes sense that they're correlated. For example, it might be total ether balance versus, the highest transaction amount. Those two might be highly correlated, which makes sense. Nothing necessarily to be done there. So really no big takeaways from here, but it's important to check. Then we do, our split of the data where we actually take the columns that we want to call features, and that's what we assign to X. Nomenclature is capital X, and small y is really the flag. This can be thought of as vectors of the features and the labels. And then we do the famous split of the data, which essentially splits both the features and the labels into the training and the testing set. We've just used the standard 70-30 split, although there are various statistical techniques and various other research that you could do to see what's the perfect split that you could do on the data. So we've already looked at some ways in which we've dropped some features based on common sense, like if all the values are 0, we're not going to use that. But there's also some statistical ways of doing that. And one of them is chi-square. The other one is ANOVA, which is the analysis of variance. Again, we're not going to go into the details of these statistical techniques for the purpose of this demonstration, but at a high level, they can be thought of as how relevant is a certain feature in determining the outcome. And things that are less relevant and have less ability to determine the outcome, we may then choose to drop some of those. And that's what's going on here. Finally, then, after all that, we can move into our classification itself. And so the first model we've used is a decision tree. So a decision tree essentially uses it creates a tree based on the features and the values of those features. And when we ask the question to predict on test data, it just uses traversal through the tree itself in order to predict an outcome. And so that's kind of what the underlying algorithm does. It first decides which feature to split on, and in this case, it uses a standard of Gini impurity, but there are various other ways in which it can split as well, including entropy and information value, etc. But here, first we create a model object, then we fit that to the train data, and we have to include both the X and the Y, because when we're training, we want to, since it's supervised, we want to give it the labels as well. And then finally we predict, and for prediction, we only use the test, and we only give it the features of the test. We obviously don't want to give it the labels. So we do that, and then we can compute the accuracy using this function that's out of the box from the metrics for sklearn, and we compute the accuracy to be 96%. Now, the thing about the accuracy that's important to understand is, if you predict in a certain data set, if you predict none of them were fraud, you'd still be pretty accurate because the number of fraud cases are usually very low. So really a more useful metric is what's called recall, which mathematically is the true positives over the true positives plus the false negatives. But a conceptual way to think about this is how many of the actual fraud did we correctly predict? And so that's the metric we're going to follow here. And so when we compute that, we can see that we have a 91% recall, which is a very good recall score. So just to see if we can do any better, we're going to try and tune this decision tree. So again, this is where I've created a customized tuning function. So essentially what this function does, and it's, there's a lot going on here, but, we use different parameters within the decision tree. Up top here, I haven't given it any parameters, any arguments, but it has a varying number of tuning parameters that we can use. Like, for example, you can use the max depth of the decision tree. And so one way to do this is to compute various different outcomes based on a series of values. And that's what this helper function lets us do. It takes in, the model name, either a DT or a LR for logistic regression or a RF for random forest, etc. And it takes in a couple of other parameters, which are then used to compute various outcomes using those parameters as a range. So that's what's going on here. This is a function I wrote myself. There is a part of it that I used external code for. I've cited that here, data science.stack exchange. This particular function within my function has been taken from this source. But otherwise, this function was created by me, and it was a lot of fun. So here then I'm just applying that function on the decision tree model, and you can see here now the recall is actually 92.28%. So we did improve our recall using this tuner. So we were successful in that. And so this is a value you can take. So it looks like with the parameter 100, and this 100 parameter is the max depth of the decision tree. We can actually go ahead and increase our. It's actually the 29. 29 is the parameter value, the max depth, that then gives us this value. And 53 is the number of false positives that it computed. So then we can look at a confusion matrix. So the confusion matrix is essentially, just giving us our type 1, type 2 errors and trying to give us an idea of that. So this is just a visual representation of what we saw above. Essentially, we do the same things that we did for the decision tree. We do that for 3 other models: the logistic regression, which after doing that here, we can see that it didn't yield a very good result. So we aren't really going to move forward with the logistic regression because it's far inferior to the decision tree already. A random forest, where we can see that it initially gave us a recall of 91, and after the tuning, it gave us a recall of 92.7. And the important thing to notice here is the false positives are just 13, which is great. So already it's better than the decision tree in that it gives pretty much the same recall, a little higher even, but really much fewer false positives. The gradient boost gives us 91.5%, and then our tuning was not able to benefit us at all. So doing an auto tune using whatever parameters are the default was better than us trying values 5 through 50. So essentially some value outside of this range is given it a better score. using more compute, we can obviously compute values way outside of this range and probably make all of these models better. So finally, we come to our conclusion here. So this cell essentially just prints out a grid of the recall scores and the false positives. And so now we can move back to our presentation and finish up over there. So these are the results there that we saw in that grid. So the decision tree, 92.29% recall, false positives 53, logistic regression 48.48% with 2 false positives. That one's a clear elimination. The random forest was 92.77 with only 13 false positives. Then the gradient boost was 87.23 with 11 false positives. So, really the thing that stands out here are the number of false positives of the random forest makes it a lot better than the decision tree, even though the recall is only slightly better. So that's the model we probably want to pick if we wanted to pick just one. In reality, in terms of how a fraud prediction system would work, is it would use a variety of techniques, machine learning classification being just one. There might be other ways. For example, you could use more standard, rule-based formats in order to say, okay, here are the rules and now predict if it's a fraud or not. And then you can take a mix of those two approaches and see what your predictions are. Within this particular machine learning framework also, you don't have to just select one model. You could select a mix of a couple of different models. And that's especially useful because if we did the math here and we did some more research, there might be an overlap between the predictions of the decision tree, the logistic regression, the random forest, and the gradient boost. But at the same time, there might also be some unique predictions in each of these. So in which case, what you want to try and do is see if you can pick some models which have a high recall, but very few false positives. So for example, if you take the random forest and the gradient boost, between the two of them, there's only a total of 24 false positives. And so, going through all of the rows that it predicted as fraud is still pretty beneficial because you'd only waste your time about 24 out of the number of times. Only 24 times will you lose the resources used to compute whether or not you actually have a fraud or not. So it's really a mix of different techniques that we can use. But for the purpose of this project, really the random forest did outshine the others. Moving on, just as a final slide here, our roadmap for what we can do with this is, keep tuning these models, maybe try different models as well. At some point, we can look into APIs so that we can really make this open to the community. People can start using this. And there's so many different use cases for how this can be implemented even before, validating a transaction, for example. So that in essence is this project. I just really want to thank Professor Nodar, who's been my advisor and my professor for this course. He's just been truly amazing. And I also just want to thank the Harvard community for this really awesome course. And thank you all. I will put this on YouTube. And if there's any questions or comments, please feel free to let me know and I will respond to them as soon as I can. Thank you all.